Let's now do some examples of integration in cylindrical coordinates. So let's recall first what we derived in the last video. We derived that the triple integral over a cylindrical box B of some function in cylindrical coordinates r theta z dv can be expressed as the iterated integral. R goes from A to B, theta goes from alpha to beta, and then z goes from C to D of f of r theta z. And remember, dz or dv, excuse me, is r dr d theta dz, right? And we saw this construction in the last video about how to take a cylindrical box, partition, like introduce your partitions of all the intervals, calculate the volume of the ijkth box, and then this gives you an approximate formula for the volume. You take the limit to get the actual volume and simultaneously the definition of the triple integral in cylindrical coordinates. And so, again, by Fubini's theorem, we can do this in any order we want. So let's see a handful of examples so we're actually more than comfortable with just the formula, but we can actually use it in practical applications. So let's take the triple integral, or so let's example here, and let's evaluate the triple integral over the box B of z r sine theta times r dr d theta dz, where this cylindrical box is sets of triples r theta z such that r is between 0 and 2, theta is between 0 and pi over 2, and z is between 0 and 4, right? And so this is kind of the most standard, one of the most standard types of integrals, triple integrals in cylindrical coordinates we can see, because all the bounds are constant and we know exactly what the function is here. So we have the triple integral over, well, r is going to go from 0 to 2. Theta is going from 0 to pi over 2. And then z is going from 0 to 4. And what are we integrating, right? We're integrating z r squared because of the r sine theta times r dr d theta dz. So we have z r squared sine theta dr d theta dz. And now we have to integrate these with respect to each variable. And so I'm going to go through this two types of ways. The first way is just our standard integration here. So the standard, when we integrate with respect to r, well, we'll get 1/3 r cubed. So double integral 1/3 r cubed z sine theta, because with respect to the variable r, z and theta are constants. And so when you take into account constants in the integration, they just go along. And so we have theta from 0 to pi over 2. We have z from 0 to 4. And we're evaluating this integrand from 0 to 2, d theta dz. If we plug in, notice if we plug in 0, we get 0. And if we plug in 2, we're going to get 1/3 times 8. So that's going to be 8/3 z sine theta. And so this goes from theta equals 0 to pi over 2. Then we have d theta d z, not d theta squared, dz. And so now let's integrate with respect to theta and treat z as a constant. So we have integral z goes from 0 to 4. Integral sign is negative cosine, so we have negative, and I can pull the constants out front, right? So I'll have negative, let's just pull them all the way out front, negative 8/3. Then we have z cosine theta from pi over 2, or from 0 to pi over 2, dz. This is negative 8/3, integral z equals 0 to 4 of z, and then it looks like we have cosine of pi over 2 is 0, minus cosine of 0, which is 1, so negative 1 dz. This gives me 8/3, integral z equals 0 to 4 z dz. And we can quickly integrate this, and I'll just stick on the same page here. This is 8/3 times 1/2 z squared, and we're evaluating this at 4 and at 0, and so that's 8/6, and then we have times 16 minus 0, which is 8/6 times 16. Well, then that's 64/3. Okay, and so here's kind of the straightforward way of computing this integral. Now, I want to show us a different way we can do this integral, and this works in any coordinate system, right? And so if we have triple integral r goes from 0 to 2, let's relook at this problem. Theta goes from 0 to pi over 2, and then z goes from 0 to 4. And what we're integrating was z r squared sine theta dr d theta dz. If we look at this, we notice this is a product of 3 variables here. And so we can write these. So r is constant with respect to both theta and z, right? And z is constant with respect to both r and both theta, and theta is constant with respect to r and z. And so because of that, we can express this integral slightly differently. We can pull constants out in front of integrals, right? And so if we're looking at the innermost integral here, which is dr, well, everything that's not r, right, if it's just a constant, then we can pull it out front. And so that means we can write this as z equals 0 to 4 times the integral theta equals 0 to pi over 2 of, and now we can pull everything out front of this integral that isn't an r term, right? And so that's z sine theta, and then d theta dz times, because we pulled all of that out front, right, times the integral r goes from 0 to 2 of r squared dr. We can do the same thing now, but just with theta and z. We're taking the integral now with respect to theta, and so anything with a z in it, we can pull out in front of the integral. And so because of that, this becomes integral z goes from 0 to 4 of z dz times integral theta goes from 0 to pi over 2 of sine theta d theta times integral r goes from 0 to 2 r squared dr. And now this is a product of 3 single variable integrals, right? Now this is a lot easier to evaluate. This is then 1/2 z squared from 4 to 0 times negative cosine theta from 0 to pi over 2 times 1/3 r cubed. R goes from 0 to 2, and you can see immediately that we'll get 64/3 again, right? And so the point is, if inside the integral, if it's a product of independent variables, right? And so like an example of when you couldn't do this is if you had triple integral sine theta plus z, or something like r times theta plus sine z, and then you did like dr d theta dz. Well, you could split up the r to where this is sine theta plus z d theta dz times r integral, or not on the outside though, of course, integral r dr. You could do this, but you can never split these variables up, right? And so there's a lot of times when you can't do this sort of a method, but there are times when it's just like the product of variables. Well, then you can use this to your advantage, that when you're taking the integral, the other variables are treated as constants. And so you can get something like, in these best case scenarios, you can get something like the product of 3 single variable integrals instead. And so that's a first look at, and again, sorry, before I go on, what I want to say is that this is not just for cylindrical coordinates, right? This works for double integrals in any coordinate system. This works for triple integrals in any coordinate system. You just have to make sure that it's the product of variables, and where each term of the product, or each factor of the product, it's dependent on only one of the variables. Okay, so now that we've discussed that, let's look at an example that will help us understand setting up triple integrals in cylindrical coordinates over general regions. So let's look at triple integrals in cylindrical coordinates over general regions. Okay. And so let's imagine a region E. So to understand how we can approach these types of problems, I'm going to start with an example. And let's consider a region E, which is inside the right circular cylinder, r equals 2 sine theta, bounded below by the r theta plane and bounded above by a sphere of radius 4. Centered at the origin. And so let's set up integral for some function r equals f theta z over e. And this is what we want to do. Okay, and so here's our example. This is a pretty good example for cylindrical coordinates because it gives us an idea of how, well, one, how to observe what surfaces look like in cylindrical coordinates, or what surfaces are represented by what functions in cylindrical coordinates. And then it also gives us a good idea of how to set up an integral over just like a more generalized region and not necessarily a cylindrical box. And so let's remember what we're looking at. So here's x, y, z, just to get ourselves oriented. And we're looking at the right circular cylinder, r equals 2 sine theta. And so if you'll remember from what we learned in graphing in polar coordinates, this is a circle of radius root 2. And so maybe this should be back like this, right? And we have this right circular cylinder. And so in the r theta plane, it's a circle, but then there's no restriction on the z value. And so we get indeed like a cylinder here. I can draw this a little better. Right, and so we get like the top half of like an infinite Pringles can, I guess. And because we're bounded below by the r theta plane, right, that's also the xy plane for intuition, right? And we're bounded above by a sphere of radius 4. And so we come up 1, 2, 3, 4 here. And I'll draw it in red. We have some sphere. And you can kind of imagine how this sphere intersects this cone. And we get, or there's not this cone, but this cylinder. And you can see that their intersection is what I'm going to draw in blue here. It's kind of, so if you imagine putting like a bowl on top of a Pringles can, and you get kind of this shaded region here, but it's three-dimensional, of course, right? And so it's like a cylinder that's been kind of cut off by a sphere at, and remember the cone here isn't centered at the origin, so it's not going to sit like perfectly in the middle. It's going to be cut off at kind of a weird angle. And we want to set up the triple integral for some function, right? And so our lower bound is the r theta plane, right? This lower bound down here is the r theta plane. What's our upper bound? Well, our upper bound is the sphere of radius 4, which is x squared plus y squared plus z squared equals 16. Now, in cylindrical coordinates, x squared plus y squared is equal to r squared. And so a formula for a sphere in cylindrical coordinates is x squared plus z squared equals 16. Okay, and so let's see what our bounds are going to be. Well, let's start with our z bounds. These seem to be the easiest. So for our z bounds, notice again, the bottom bound is the r theta plane. The r theta plane is at z equals 0 because it's the same as the xy plane, right? And so our lower bound is 0. And then our upper bound is a function, right? How high we can be from the r theta plane depends on our r and theta coordinates. Or more precisely, not even our theta coordinates, just our r coordinate. And so because of that, we have this function that's describing our bound, and it's z squared equals 16 minus r squared, or z equals root 16 minus r squared. And so our upper bound is root 16 minus r squared. All right. We also need, now we need our r bounds here. Our r bounds are saying, okay, well, how far out from the origin can I go, right? And if you'll notice, this depends on theta, right? Because what are we looking at? In the r theta plane, or any trace parallel to the r theta plane, the picture we have is a circle of radius root 2. This is r equals 2 sine theta, right? And so our radius depends on theta, right? However far out we can go from the origin depends on what angle we're taking this line in. And this function is given by r equals 2 sine theta. And so that means our lower bound is 0, which is the origin, and our upper bound is 2 sine theta. And lastly, we need bounds for theta, right? What are our bounds for theta? Well, we can look at this picture again here, and we notice that the graph of r equals 2 sine theta includes nothing in octants 3 and 4, or in quadrants 3 and 4, right? And so because of that, theta can go from 0 to pi. And so these are our bounds now. We have these bounds here. And this is how we describe the region E, right? This is E, right? And the last thing we need to do is set up the integral. And when we set up the integral, remember, we have to set this integral up in an order such that a variable with bounds that depend on another function or another variable, those must come after, right? So setting up the triple integral of this arbitrary function, f of r theta z, r, d. So now let's pick the order here, right? Well, so we're looking at our z bounds, and I see that my z bounds depend on r, and then my r bounds depend on theta, and then my theta bounds are constant, right? And so whichever bounds are constant, I know has to be last. So theta goes from 0 to pi. And then z depends on r. The z bounds depend on r, which means I need to integrate z before I integrate r. And r bounds depend on theta, so that means I need to integrate r before theta. And so since theta's last, and I have to integrate z before r, we know this will be r z. And so we'll have dz, dr, d theta. And z went from 0 to root 16 minus r squared, and then r went from 0 to 2 sine theta, and then again theta goes from 0 to pi. And so this is my setup of this integral. And now you can see, hopefully this is a pretty good example for how you approach setting up a triple integral in cylindrical coordinates over a general region. You kind of look at the information that's given, like what we're bounded by, right? We're bounded by 2 sine theta. We're bounded below the r theta plane, bounded above sphere of radius 4. You take all of these pieces of information, turn it into our equations and pictures that we can understand, and then from there you can argue what the bounds should be. And then once you know what the bounds should be, you can set your integral up. Okay, and the last thing I'd like to talk about in cylindrical coordinates is switching the order of integration, because Fubini's theorem says that we can integrate these. We can take the triple integral in any order we want. But again, just as it's been seen in double and triple integrals now, if your bounds have functions, then you cannot interchange them without some work as rewriting the bounds. So let's look at an example of how to interchange the order of integration while still keeping bounds as functions. So let's let E be bounded below by the cone z equals root x squared plus y squared, and above by the paraboloid z equals 2 minus x squared minus y squared. Let's set up triple integrals in. All right, so let's set up triple integrals to find volume. In the following orders. So let's do A will be in the order dz, dr, d theta, and then B will be the order dr, dz, d theta. Okay, so let's first, again, understand what's going on here, right? We have a cone, z equals x squared plus y squared. So the cone z equals x squared plus y squared looks something like this. Okay. And this is what's bounding us below. What's bounding us above is the paraboloid z equals 2 minus x squared minus y squared. And so you come up to 2 here, and we have some paraboloid. It's going down like this, right? It's not a sphere. It kind of looks like it, what I'm drawing here, but it's not. It's a paraboloid. It goes down infinitely like this. Okay? And we want the region E is the region that's bounded by the cone and this paraboloid. And so it kind of looks like a snow cone, right? Or like a frozen ice thing here, because you have your cone, and then you have this rounded part at the top. And so we want to set up integrals in 2 different orders, given here and here, to find the volume of this region. Okay. And so if we want to integrate with respect to z first, so like let's look at A, right? We need to know where we start and where we stop traveling in the z direction, right? Well, where do we start? Where we start depends on these angled lines right here, right? And these angled lines are the cone z equals root x squared plus y squared. Well, in cylindrical coordinates, x squared plus y squared is r squared. And so this is z equals r. And so what this means is this cone is however far you are up, that's what your radius is, right? And so it's a pretty nice cone. Like I'm at a certain z height, well then that's the radius of the circle of the cone at that level. Okay, what's next? What's our upper bound, right? Our upper z bound is this paraboloid. And so the paraboloid was given by z equals 2 minus x squared minus y squared. Well, you'll notice that this is equal to 2 minus quantity x squared plus y squared, which in cylindrical coordinates is 2 minus r squared. And so because of that, we see our lower bound for z was r, and then our upper bound was 2 minus r squared, right? Because the lower bound is this line, which is z equals r. And then the upper bound was this paraboloid, which in cylindrical coordinates is 2 minus r squared. And now we need a formula, or we need bounds for r, and we need bounds for theta. Well, the theta bounds are easy, right? There's no restriction into what direction we're traveling, right? This cone sweeps around all 360 degrees. So here our theta bounds is just from 0 to 2 pi. Okay, and then the last thing here we need is our r bounds, right? And so we need to find, well, the first we can tell is when r is going to be 0. We can see that because we're including the origin. And then for the upper bound, we need to set, like, what's the biggest r we can have, right? The biggest r we could have is all the way out here, where part of the circle is their intersection. And where do these two functions intersect? Well, they intersect when their formulas, this formula and this formula, are equal, right? And so they intersect when 2 minus r squared equals r. In other words, r squared plus r minus 2 equals 0. Well, this is r plus 2, r minus 1 equals 0. And we know r is a positive value. And so that means we can't have r equals -2. So we must have that r equals 1. And so our upper bound here for the radius is 1. And then we can set up the volume as the triple integral. And we're going z from r to 2 minus r squared, r from 0 to 1, theta from 0 to 2 pi of dv, right? You just integrate the constant function 1 to find volume. And so this is r dz dr d theta. So that was part A, right? And now we want to change this order of integration so that we're integrating something in the order, what was B? Let's see here, dr dz d theta, right? And I'm going to redraw our picture here. And I'll draw just the bounded region. So we have something like this. And if you'll notice, at the level z equals 1, like we want formulas for the bounds, right? We need, like, we want first r bounds, then z bounds, and then theta bounds. Well, the theta bounds are easy, 0 to 2 pi. Nothing's changed there. And now with the z and the r bounds, well, if we want to do r first, then r should be a function, right? Or the bounds for r should be functions. And then our z bounds should be constant. Well, you notice when at z equals 1, this radius, the function that's defining the outer bound switches, right? When z is between 0 and 1, the outer bound is the function z equals r. But when z is between 1 and 2, we get something different, right? We get the outer bound is this paraboloid and not the cone. And so because of that, when we switch the order, we have to break up the integral. So z goes from 0 to 2, but r depends on whether z is between 0 and 1 or 1 and 2. If z is between 0 and 1, well, then the radius is given by this function here, which we know is the function z equals r. And so that means r is bounded between 0 and z, right? And then what about the upper half? When z is between 1 and 2, well, then r is bounded by, well, we had, this was the function z equals 2 minus r squared. So solving this for r, we get r squared is equal to 2 minus z, and so r is equal to root 2 minus z. And so when z is between 1 and 2, we have that r is between z, or sorry, 0, right? Because you can still have radius 0. Like the z axis here is r equals 0. And then like the radius outward is root 2 minus z, root 2 minus z, right? And so now this volume is the triple integral where r goes from 0 to z, z goes from 0 to 1. So let me just write this on a bigger page so we can see this. R goes from 0 to z when z is between 0 and 1, and then theta goes from 0 to 2 pi of the volume, which is r dr dz d theta. But then this is plus when z goes from 1 to 2, we know r went from 0 to root 2 minus z, and then theta again went from 0 to 2 pi. And then this is r dr dz d theta, and this is a formula for volume in the different order. And so hopefully this gives us a decent idea of what switching order of integration in cylindrical coordinates looks like. It can be a little complicated, especially when you have to split up an integral into two integrals based on like a z value or something like this. And so this concludes everything I wanted to teach over integration in cylindrical coordinates. And the next two videos are going to be an analogous approach, but now for integration in so-called spherical coordinates. And in the next video, I'll define what spherical coordinates are, and then we'll again go through the construction of the triple integral and see a handful of examples so that we feel comfortable taking integrals in any given coordinate system.